Hello, ladies and gentlemen. Today we're going to be taking a look at what is called real numbers. So in the past, you've learned that a number is a number and it doesn't belong to a certain set of groups. You've just been working with those numbers and using them to answer equations and things like that. Today we're going to start classifying numbers. So all numbers are part of what are called the real number set. So real numbers are all numbers, and we can use the letter R to represent that set. Within the real numbers, there's a whole bunch of other types of number sets. So one of those groups is what we call rational numbers. That can be represented by the letter Q. And those are numbers that can be written as a ratio or fraction. So any number you can turn into a fraction is a ratio. So for example, 0.5 is 1/2. It is a ratio, therefore it is rational. 0.3 repeating is 1/3. It is a ratio, therefore it is rational. The number 8 can be written as 8/1. It is a ratio, therefore it is rational. The number -25 can be written as -100 divided by 4. It is a ratio, therefore it's rational. Irrational numbers, on the other hand, written or represented by the letter I, are numbers that cannot be written as ratios. Those are non-repeating, non-terminating decimals. So things like pi, for example. Okay, pi is that symbol for 3.14159, which helps us work with circles. Okay, that number would keep on going and going and going, never stop, never repeat. Therefore, it is irrational. Another example would be something like 0.05000500050005. So it looks like it has a pattern, but it's not really repeating. So that one is irrational. Another example is when you try to take the square root of a number that is in a perfect square, which we're going to talk about more later. So for example, the square root of 20, there is no number that multiplies by itself to get 20. And if I take my calculator and do the square root of 20, so I do 20 square root, I get 4.47213595499. Nowhere in that long strip of numbers do I have a repeating set of numbers. So it is also non-repeating, non-terminating, therefore irrational. Then within those numbers, there are some more sets. So we have natural numbers, which are the counting numbers. Those are the numbers you naturally start counting with. So for example, when you start to count, you always start with 1, 2, 3, and so on. It's nothing in between, just those natural whole numbers. Whole numbers, which I just mentioned, that's W, are the set of natural numbers and 0. So I like to say it's the set that starts with a whole. So 0 has a hole in it. So it's all the whole numbers from 0 and up. Integers we use Z for, and those are the set of whole numbers and their opposites. So all your positive and negative whole numbers. So there are all the types of sets that we have to learn about and be able to discuss. All right, so now, furthermore, we have to understand square roots and be able to put those in number sets. So we have, when the square root of a number results in a whole number, it is rational. If the square root of a number is not a whole number, it is irrational. So that's like that square root of 20 that I talked about before. Square root of 20 is irrational because you cannot take its square root and get a whole number. Where square root of 25, if you take the square root of 25, it equals exactly 5. So that would be rational. So I'm going to do some of the next examples with you, and then you're going to try the last 4 on your own. All right, so it says determine the square root of each of the following, round to the nearest tenth when necessary, circle the rational numbers. So I kind of did this one already with you. We have negative square root of 25. So you should know that the square root of 25 is exactly 5. Therefore, the negative square root of 25 is negative 5. So this is rational. So we're going to circle it. I'm also going to write it underneath. Okay, the next one is the square root of 121. Now, if you're not good with your square roots, we're going to make sure we practice those a lot. It would be helpful to know them, but you might not recognize whether it is a perfect square or not. So we're going to go into our calculator, do 121 square root, and we get exactly 11, which means that this is also rational. Then for square root of 90, we get 9.4868329800050513 dot 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 dot. It keeps on going. It never repeats. It never ends. If our calculator screen was really, really long, that number would continue infinitely. It's what we call an infinite decimal expansion. So we're going to round it to the nearest tenth. So it is about 9.5, and it is irrational. Okay, next we have this negative square root of 12. So we do the square root of 12, and we get 3.4641016 dot 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 dot. No repeating pattern, therefore I can't write it as a fraction. Therefore, again, it's irrational. Rounding that to the nearest tenth, we get about 3.5, and we're going to make it negative because of the negative sign out front. And again, this one is irrational. So I'm going to do one more with you before letting you be on your own. Square root of 400 is exactly 20, because 20 times 20 is 400. So therefore, this one is rational. So you can pause the video now and do 6 through 9, or wait and come back to it at the end of the video. I'm going to move on to the back. All right, so on the opposite side, we have a graphic organizer that we're going to complete to help us determine what number sets all numbers belong in. So here at the very top, all numbers are in the number set, real numbers. All numbers are real. Then within the real number set, we have two main categories. We have the category of numbers that can be written as fractions, and the one that says that numbers cannot be written as fractions. So rational numbers is the category that contains all the other sets, and irrational does not. Then within the rational numbers, there are three other sets, from least or from greatest to least. The number set that contains the most to the number set that contains the least. We have to go down the line. So rational numbers is going to be the set that contains more numbers, because a lot of numbers can be written as fractions, even though you wouldn't always write them that way. Within rational numbers, the next greatest group is integers, because that's your negative and positive numbers. And then within integers, we have whole numbers, 0, 1, 2, 3, and so on. And within whole numbers, we have natural numbers. Now, the only number that natural numbers does not have that whole numbers has is 0. So the only time you wouldn't start at natural numbers if you have whole numbers is when you have 0 as your number that you're looking at. All right, so we're going to go through this list and be able to now determine what number sets all numbers belong in. So you're going to keep that. Refer to it as I'm going through each number. And I'm going to do the first 5 with you, and you're going to do the last 6 on your own. I think I'm doing the first 6 with you, and you're going to do the last 6 on your own. All right, so for number 1, we have negative 6. So negative 6 is a negative whole number. All right, so it's a negative whole number, so it doesn't belong in the whole number sets. The smallest group it would fall into is integers. And then we follow our graphic organizer up from integers. Integers is in the rational set, so it's also rational. And rational is in the real set, so it's also real. So negative 6 belongs to integers, rational, and real numbers. Now you might be thinking, well, how do I write negative 6 as a rational number? Negative 6 over 1 is a fraction, therefore it is rational. Okay, number 2, we have 8 and 2/5. 8 and 2/5 has a fraction attached to it. It's not a whole number. Okay, so it's not a whole number, and it's not an integer because of the fraction piece. Okay, once you have that fraction piece, the first place it can fall into is rational. So this is going to be rational and real, because 2/5 can't be changed to a whole number either. That is 8.4, so it's just rational and real. Pi we talked about earlier. Pi is a non-repeating, non-terminating decimal. Therefore, it is irrational, but also real. All numbers are real. All right, square root of 2. So here, you're going to use your calculator again. We do the square root of 2. 2 square root. We get 1.414213562373 dot, 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 dot. Nowhere in there is there a repeating pattern. It is an infinite decimal expansion that cannot be written as a fraction. Therefore, it is irrational, but also real. Next one, 5.3 repeating. 5.3 repeating repeats, therefore it's going to be rational and real. So whenever you see something repeating, think rational, R with R. Something else that's a real quick trick that you can remember, 0.3 repeating, hopefully you remember, is 1/3. So there's your fraction. But any number that repeats once can be written over 9. So for example, 0.1 repeating equals 1/9. And I can prove it to you by doing 1 divided by 9 in my calculator. I get 0.1 repeating. So 0.2 repeating is going to be 2/9. 0.3 repeating is 3/9, which simplifies to 1/3. 0.4 repeating is 4/9. 0.5 repeating is 5/9. So that's just a real quick way that you can change a repeating decimal into a fraction and prove that it's rational. The same thing actually applies to double-digit repetition. So for example, if you have 0.45 repeating, that's 45 over 99. If you have 0.61 repeating, that's 61 over 99 because there's 2 digits repeating. So just a real quick fact there that might help you set those equal to fractions in the future. All right, so then the last one that I'm going to do with you is 0.05. So that is a fraction because I can write it as 5 over 100 because the 5 is in the hundredths place. Okay, it's definitely not a whole number or an integer, so it is just rational and real. All right, so you're going to do 7 through 12 on your own. Make sure you're answering the questions in GoFormative as you go and that you fill in all of the incomplete parts for today. Have a nice day. See you later.